Welcome to the third session of the day. Our first speaker will be Lioba Heimbach from ETH Zurich.
Yes, so thank you for the introduction and thank you for inviting us to give the talk here. So I will be talking about optimistic MEV in Ethereum layer 2s and as to why this just might be the answer, why their Blockspace is always in demand. So my name is Lioba, and this is joint work with Ozan, Jan, and Roger. And Jan is actually also in the audience today, so if you have any questions after the talk, you can also ask him. We're all from ETH Zurich. In this space, this sometimes leads to confusion. This is ETH, the university, not ETH, the cryptocurrency. But now Jan is also joining the Ethereum Foundation, which just might really add to the confusion even more. So with that, let's look at what I'm going to be talking about today. So now we're talking about Ethereum, the blockchain, and Ethereum in the past, it had problems with scalability. So high demand on the Ethereum layer 1 just led to there being an increase in transaction fees and congestion on the network. So instead of just making the layer 1 bigger, what Ethereum decided to do is to also adopt a roll-up-centric roadmap. What this means is that we move transaction execution, at least for a good proportion of transactions, off-chain to layer 2s. And these layer 2s, they then post their data to the layer 1. So the layer 1 is essentially a settlement layer for the layer 2. And then it is thereby securing these layer 2 chains. Now, transactions on the layer 2s were already a lot cheaper than on the layer 1. But last year, then the Denkun upgrade, as part of that in EIP 4844, blobs were introduced, which made layer 2 transaction fees even lower. These layer 2s, they're really gaining traction. They're no longer experimental. In the first quarter of this year, actually, around 50% of the DEX volume in the Ethereum ecosystem has been on these layer 2s. And also, they are securing more than $40 billion in value. But despite this, we really do not understand much about how this MEV landscape differs on the Ethereum layer 2s as opposed to the Ethereum layer 1. So I want to start by pointing at some differences between the two that might then also lead to their differences in the MEV landscape. So the first one is fees. On the layer 1, we have, at least in comparison, high fees, while layer 2 fees are quite low, and they've gotten even lower with blobs being introduced. Then block times. In comparison, the layer 1 block times are currently quite long. There's a block only every 12 seconds, while it's 2 seconds on the OP stack, so Optimism and Base, and around a quarter of the second on Arbitrum. Now, the last difference I want to point out that might be relevant for how MEV might behave differently in these two ecosystems is that on the layer 1, the way transactions are ordered, it is done by builders essentially. So most blocks on the layer 1, they're built through a builder auction where builders are optimizing blocks. So they're reordering transactions to build high value blocks, so high MEV blocks. And on the L2s, this is not quite what is happening. There we have sequences. On Arbitrum, this is first come, first serve. So transactions are ordered just in the order that they came in. This was at least until the introduction of Time Boost, which gives some transactions priority, but our data largely predates the introduction of Time Boost. Now on the two OP stack rollups, we have gas auctions. So the transactions in a block are just ordered by how much they're willing to pay, essentially. So these are some of the differences between the layer 2s and the layer 1. And what we found is that these differences really fundamentally change the MEV landscape on them. And let's very quickly say what MEV is, even though I'm sure this audience doesn't need it. But it is essentially the value that you can extract through including, excluding, and reordering transactions in a block. Now, common examples that we've in the past studied on the layer 1 are sandwich attacks, cyclic arbitrage, sex-dex arbitrage, or liquidations. But now the thing that I want to get at here is that on the layer 1, these MEV opportunities, they're generally computed off-chain. So you compute some profitable sandwich attack, cyclic arbitrage, then you put your bundle and you include it generally, at least through the PBS auction these days, and then it will only make it on-chain if it is profitable, essentially. So there is a lot of precision and pre-planning involved in MEV on the layer 1, at least in general. So to show it more as an analogy, let's assume that we have a really big fish here. All fishers, also the ones in the boat, they found this opportunity, but then one of them essentially buys the right to go into the ocean with the harpoon, and it's a special harpoon that just is able to kill every fish it sees, and thereby sort of get this big profit it has. So this is traditional MEV as we know it from the layer 1. And then when we move to the layer 2, this is maybe more what it looks like. So we have all these fishers that are just putting in their fishing rods without really knowing whether there are any fish. There are some tiny fish around. Most of them will really not catch any fish, but they don't care because it's so cheap to just sit there and keep fishing, even though the chance of them actually getting a fish is quite low. So this analogy was supposed to hint at the difference between traditional MEV on the layer 1, which is very precise and of high value, and optimistic MEV on the layer 2, which almost has this spam-like feature. So to put it a bit more formally, by optimistic MEV, what we mean in this work are essentially strategies where the profitability of a transaction is searched for and decided on during the on-chain execution. And this then leads to many speculative transactions that often end up executing without actually executing any trade or executing upon any MEV. Now, in this work, where we study optimistic MEV, we in particular focus only on cyclic arbitrage. The reason why we do this is that with cyclic arbitrage, you can search for the entire opportunity in a single transaction on-chain and then also execute it in a single transaction on-chain. So essentially what this means is that you can discover the profitability during execution time, which isn't the case generally for the other types of MEV. So now let's look again at how traditional MEV looks. Now, in particular, we're looking at cyclic arbitrage here. So this is just one cyclic arbitrage that was executed on the Ethereum layer 1. And what you essentially see here is that we have this bot here that makes a profit in wrapped ETH by also going through another token. But the crucial thing here is if we look at the call data, which I'm showing up top, the pools are specified, the amounts of the trades are specified. It's all in the transaction call data already. This was pre-executed. This transaction didn't land the chain and was first wondering what it should do. It had exact directions on what to do. Now, let's look at how a cyclic arbitrage transaction looks on the layer 2s, which is one that is in this optimistic MEV world. So first, it looks quite similar, right? We also have a cyclic arbitrage bot here that has the starts with wrapped ETH and then makes a profit in wrapped ETH, just goes through one additional pool essentially. But the difference really is that if we look at the call data now, it is completely non-informative. And this suggests that this wasn't pre-computed. The transaction was actually searching for these opportunities on-chain. So that logic was in the smart contract and the computation was happening on-chain with this optimistic MEV as opposed to off-chain, which we saw with the traditional MEV. Now, the question we were wondering, once we saw that there were these transactions which seemed to be just determining the profitability on-chain, so optimistic MEV, what does it really look like on the layer 2s? How big of a thing is it? And for that, we first needed to collect data. So we collected raw blockchain transaction data from the Ethereum layer 1 to have something to compare against. And then from 3 layer 2s, which are Arbitrum, Base, and Optimism. And these are just the biggest 3 layer 2s in terms of volume and total value locked. Then what we did next is on all of these 4 chains, we detected cyclic arbitrage contracts. So we went out and searched for contracts that perform cyclic arbitrages, so bots essentially that do cyclic arbitrages. And then most importantly, we then with this were able to classify transactions. So for each transaction, we classify it along 3 dimensions. The first is the purpose. So is the transaction a cyclic arb transaction? That means it was submitted by one of these cyclic arbitrage transactions or not, then it's other. Now, the second dimension is the DEX involvement. And there we differentiate between three different things. The first is if the transaction actually executed a swap on a DEX, then we call it trade. The second category, interaction, that is transactions that we see, they're reading the DEX state, but we do not see them actually ever executing a trade. So they are interacting with a DEX, but not doing a trade. That is the interaction category. And then we also have residual. These are just the transactions that do not even interact with a trade. And now the third dimension that we label is execution outcome. That just means whether the transaction successfully executed or whether the transaction reverted. Okay. So as I was saying previously, one of the defining features of this optimistic MEV is really that it is quite speculative. When the transactions are being submitted to the chain, you do not even know what the opportunity is, neither do you know whether you will actually be the one capturing the opportunity if it were to exist. So what I'm showing on the slide now is that as a result of that, the outcome of transactions from these cyclic arbitrage bots, they are radically different across the chains. So for each of the 4 chains we looked at, what I'm showing on the slide is essentially for those transactions that are being submitted by these cyclic arbitrage bots, how many of them actually perform a trade. Presumably, this is a successful cyclic arbitrage. Those are shown in red. Then in orange, I'm showing those that actually interact with a DEX. So they read the state, presumably that computing whether anything profitable exists. But then in orange, essentially, it's those that do not actually revert. They just eventually stop executing. And in yellow, it's the same, but these are the transactions that then stop executing. And what we can see here is that on the 2 OP stack rollups, so base and optimum, less than 12% of the transactions from these cyclic arbitrage bots, they actually succeed in executing a trade. So more than 98% of them, they just do not do anything. They do some on-chain computation, but nothing really comes out of it. And this is extremely different to Ethereum, where more than 95% of transactions from these cyclic arbitrage bots actually perform a trade. Now on Arbitrum, it sits somewhere in the middle between these OP stack rollups and Ethereum. There we have a pretty equal 50-50 split. With 50% of them, they actually execute a trade, and then the remaining, they decide to not execute a trade because, well, they couldn't find an opportunity, for example. So this really shows the difference that this behavior in optimistic MEV versus traditional MEV does to the outcome of transactions. What we then wanted to do next is we wanted to understand what is the scale of this. And for that, what I will be showing you is the daily gas usage on these 4 chains. So for now, what you can see in here is essentially all the gas usage by transactions that are not from cyclic arbitrage bots. So this is essentially the part that we didn't really look at too much. And now the first thing that I will add in is the cyclic arbitrage trade proportion. So now this is the gas usage by cyclic arbitrage bots that actually do perform a trade. And really, when we're looking at this, we don't see radical differences between these chains yet. The proportion of cyclic arbitrage trade category is actually relatively similar across them all. Note that Arbitrum just looks a bit different because of the scale, but overall, it is all quite similar. Where we do see the radical difference now is when we include the cyclic arbitrage interaction category. So that is what is shown in orange now. And essentially, these are the transactions from cyclic arbitrage bots. They presumably want to perform a cyclic arbitrage, but they just read state and eventually they stop without ever executing upon any opportunity. And here you really see the radical difference between especially the OP stack rollups and the Ethereum layer 1. Now, in total, in the first quarter of this year, the optimistic MEV, so the cyclic arbitrage bots, in total, they accounted for 55% of gas on optimism and 51% on base. On Arbitrum, it was 7%. But I think the more important part here is that on base and optimism, actually around 50% of the total gas usage is then the cyclic arbitrage interaction category. So this is just pure on-chain searching or on-chain computation where no trade actually executes. This is something that to some extent wouldn't even need to be on the chain. But still, on these two OP stack rollups, it is currently accounting for around 50% of the total gas usage. And what you can also see is that in this plot we're showing with the dashed black line, the blob, the gas target as it's evolving. And you really see that this optimistic MEV from these cyclic arbitrage bots, it is filling up the blocks. There seems to be almost an unlimited demand for Blockspace from these low-cost speculative types of transaction, especially on base, and on optimism this has recently also been the case where it's just filling up the blocks essentially. Now we know that these bots on the two OP stack rollups, they are consuming around 50% of the gas. What we then also wanted to see, are they paying around 50% of the fees? For that, what we did is we compared the average gas price on base and optimism for the cyclic arbitrage bots that's shown in orange, and then for the others, we're showing it in blue. And what you can see here is that they are underpaying. So they're paying 3.5 to 6 times less than others. So all the other transactions on average on the two OP stack rollups. Additionally, this is what I was pointing at previously already. What we find is that once we were adding additional block capacity to especially the two OP stack rollups after the Denkun hard fork, this was mostly consumed by these cyclic arbitrage optimistic MEV transactions, and it wasn't being used by ordinary users. So they weren't the ones that were profiting from this new block capacity. So knowing that this is quite a significant phenomenon on the layer 2s, we also wanted to understand a bit more as to what drives this. And for that, we did a regression analysis, and essentially we were able to identify 3 clear drivers of both optimistic MEV activity, as well as those transactions that are actually successful. So the first one is the Ethereum price volatility. This intuitively makes sense because when prices are volatile, they are moving more rapidly. That means that price differences are just more likely to also occur with a higher frequency. And that would then mean that for one, these optimistic MEV transactions might be more likely to be successful, but also that they would probably spam the chain even more, submit more transactions to take advantage of these fleeting opportunities. Then the other thing that we find to be driving optimistic MEV activity is retail trading volume. The reason for this is that retail trading volume, it is not as optimized. So it tends to potentially be more likely to leave some price differences after it executed if like a non-optimized trade is being executed. And what that then means is, again, we have more price differences where the optimistic MEV comes in. And the final factor we found, it is quite related to the previous one. This is a lower DEX aggregator usage. So amongst the retail volume, sort of what proportion of them is using DEX aggregators, which would mean that they're still relatively optimized, and what proportion is just submitting, well, as they are without an aggregator, which then would again mean that they are more likely to leave these price differences, which is good for optimistic, which then drives this optimistic MEV activity. Okay, so what I want to conclude with is to talk a bit about what the impact of optimistic MEV is on the ecosystem. I think the first thing to note is that it has a significant impact. I think this is quite clear, given that it really is dominating gas usage. It's more than half of the gas usage on base and optimism, and it is really filling up their block space with these low-value probes, which are doing on-chain computation, but end up not even executing anything. But this leads but then now what this means is that we are storing all these transactions on-chain, which to some extent, they never needed to be on-chain. But the result of that is that it increases node storage demands, it increases the bandwidth load on the network, and this is then potentially also a centralizing driver in this ecosystem because there will be less players around that have the required hardware to follow these chains. And then finally, this is a very different type of MEV than what we're used to. It is of low value, it's very speculative, and this also means that it might pose some challenges to mitigate, that we cannot just plug in sort of those mitigations that we're used to from the layer 1. For example, for auctions, I would presume if they were implemented, these optimistic MEV bots might just really spam the auction with bids, which will make it harder sort of to actually build blocks. And the auctions also need to be run in shorter periods of time, given the shorter block intervals on the layer 2s. So with that, I just want to conclude by saying that optimistic MEV, it is here. It is taking up 50% of gas usage on the 2 OP stack rollups. And yeah, let's see what you think about it.
So this is a question/comment. I think that another really big reason for the difference in like unsuccessful optimistic MEV between Optimism Base and Arbitrum would be that Arbitrum actually gossips pending pending transactions via on their sequencer via WebSocket, whereas Base and Optimism don't do that. So it's much less profitable to spam or like necessary to spam the Arbitrum sequencer with optimistic MEV swaps because you know that they won't hit if there hasn't been anything previously in that block, and you can just like wait, or you know how many swaps are already in the block and like what they're likely to be, which I think it's kind of interesting because it's kind of contrary to like what a lot of people say about how we should be minimizing the effects of spam on like L2s. And a lot of times people like bring up that we should be getting rid of FIFO and stuff like that, but Arbitrum is very FIFO focused. So maybe like FIFO plus like public pending trades is actually a really good way to lower spam rather than having like a stronger privacy guarantee, but also having FIFO. So yeah, just kind of I wonder what you think of just that like line of reasoning.
No, that makes sense. I think we also talk about it a bit in the paper where I have the QR code here, that essentially Arbitrum being FIFO also means that you do not know potentially sort of exactly, or it is a bit more difficult for you to then go exactly where you want in the block versus then with the priority gas auctions on the OP stack rollups, what you would do or what we see them doing is they just bid quite lowly. They're at the end of the block. They know there's something in front of them. They don't know what exactly it is, but they want to be the first ones to take advantage sort of after it happened. And essentially this behavior isn't quite the same on Arbitrum. Like we do not know exactly what is the difference between the very different behavior on Arbitrum and the OP stack rollups. I think there's many differences and they all end up adding up with each other to create this quite different picture where Arbitrum almost looks more like the layer 1.
Thanks, Lioba. Can I ask something for the orange and the yellow transactions, which are some of those, like both of them interact, but they don't trade. One type of them reverts and the other doesn't. Do you know why one type reverts and the other doesn't, or no?
I think the reason for this, I cannot tell you exactly why. I can just tell you those on Arbitrum, we have quite a significant proportion that reverts, while on the other Base and Optimism, almost none of them revert. On Arbitrum, these are actually, I would call them a bit less optimistic MEV type transactions. For these bots that are doing them, still around 50% fail, which is still quite a bit, but they sort of fail quickly. Like they don't spend all this money on on-chain computation, which on Arbitrum tends to be also more expensive than on the 2 other rollups. And then they decide to just quickly fail and revert. So maybe they have like 1 or 2 possible things they want to check. They check those and then they are like, okay. Versus on the 2 OP stack rollups, they just seem to be searching, and eventually they stop. Exactly what is the reason for this? We don't know though.
I just found interesting that some stop without reverting. I guess that was like.
Yeah, to us, this was also surprising. I think this is how we first realized that this was going on, because we were seeing all these transactions, I believe back then on Optimism, that were using so much gas and doing nothing and not even reverting. But then, yeah, I guess there's no need for them to revert. I presume that is the reason.
And then also a second question for the average price paid that you showed later. Is this priority fees or
No,
the sum?
this is the total fee they're paying.
Mm-hmm.
So this is everything that they're being.
Okay, thanks.
And we'll take one more and then I'll ask the rest for coffee break.
Yeah, I mean, maybe one thing I'll comment on the Arbitrum one is says everyone pays the same fee. So you can't have like differing fees between transactions. But I have two questions. The first is, did you work out the total number of addresses doing this? For example, is it like a few bots or is there like 1,000 bots? Like, is it like I assume they're using like an address per bot probably. Then the second question is, did you compute the total profit they were making and then compare it to the fees they were paying? Because I'd assume if you're spamming half the blocks, and you're paying fees for this, I assume, then their profit must be through the roof if you can just afford to like waste all this block space.
Yes. So to your first question, yes, that we looked at, and it's very few that are sort of dominating the gas usage. I cannot tell you exactly what it was, but I believe on 2 of them, much more than 50% was by 10, versus on 1 of them, it wasn't quite as centralized. We also actually found that the same contracts were being reused on multiple chains. So on the OP stack chains, it was sort of the same contracts that were being reused, even on Unichain, which in theory has revert protection. But even then, they were just stopping execution without reverting, because they were reusing the same contracts they were running otherwise. In regards to profit, no, this we didn't look at. I believe their profit is not through the roof, as you put it, but I believe they are profiting, otherwise they wouldn't be doing it. But the transactions they're paying also aren't adding up too much. So, I believe they are for sure profiting. They wouldn't be doing it otherwise, but we didn't look into it because there's so many weird tokens involved in it.